Hello everyone. This is the topic of my today's presentation, Smart Filter and Smart Smoothing, a newfangled development in denoising a data-driven system. So let me first say something about the objective of the present work. As you can see here, the present work actually tries to propose a comprehensive mathematical discussion on firstly the position interactive data filter and data smoothing. Here what we have done, basically the following particulars are taken into account. The very first thing is the interaction between the current allocation point and the distant point. The second point is the contribution of current allocation point, and the third one is the contribution of distant point at each level. And the issues of the positional importance and convexity are carefully considered here also to have a more convincing strategy of denoising. And this newfangled development in this process of data denoising is coined as smart filter and smart smoothing respectively. I will just discuss on these issues later on. And to be noted that the proposed smart filter as well as this smart smoothing are here composed as a process of linear denoising one. So to start with, let me start something about these data filter and data smoothing as the introduction. After that, we will proceed further for this newly development system. So let us consider a discrete data of finite size, say capital N, and it is being actually expressed in the form of say xi within brackets I1 to n. That means the discrete data are given serially as x1, then x2 up to xn. And let us suppose parallelly that these refined data in the process of denoising, either by filter or by smoothing, it has been expressed in the form of fi starting from I1 to n. So it is being expressed in the form of f1, f2 up to fn. It is meant. Now, whenever we are talking about the process of filter at the very beginning, how we represent, we make some kind of initialization, like we suppose up to a certain level, say I1 to k. Let me fix the matter, that is what is actually coming as the filtered value. They are very similar to the observed values. So I can tell here that this is going to be fi, this is equal to xi for this I1 to k. But after that, when we proceed further, starting from k plus 1 up to the nth, the last one, we can arrange some kind of linearity here. That is a kind of linearity that is being proposed by taking the previous value. Some of the previous inputs are taken together as a linear sum, its weights are there, and we are having some new values accordingly. So these FIs are now expressed in the form of something summation from J0 to K prime, and these things are there wij x I minus j. So these w's are supposed to be the corresponding weight values, and these x are, these are the some distant values. For example, if I put j0, that is the current allocation xi, but when I put j1, that is the previous one xi minus 1, and j2 means xi minus 2, previous to previous. This way it goes, and it is going in the backward direction. And this k prime, what we have taken the upper limit of the summation that lies between these starting from 1 up to some k, what we have proposed here at the initialization. So this is actually the structure in general we can propose for a linear process of filter. But whenever we are talking about the smoothing, it is something different. What kind of difference is there? You can see here the same FIs are taken in xi. The initialization is being up to done the first k number of terms, so I1 to k. But later on, we put here this summation for the I is equal to k plus 1 up to this n values in this process. Same wij xi minus j's are taken, but the summation is taken from j0 and up to this I minus 1. That means here what we are rolling, we are taking this summation up to the very first one. That means whenever I put this I minus 1 at xi minus j value, so it would be coming as x1. That means wherever we are at this process of smoothing, we are counting all the positions starting from the very itself up to the very first one. So here we are taking the chain starting from the very first observation up to the current one. But in the process of filter, we may not take it that way. We can take some particular strip of that one, and we arrange this particular linear sum into that portion, not for the entire band what we have at this moment. So this is actually the difference between these filter and smoothing to say in this process. Now the matter is this particular technical load. Let me first put it forward because I have to say something after this. What is happening? These wij, These are the corresponding weights at the subsequent places of filters or smoothing, whatever we say. And if in a filter there is no dependence of these I in the weights, then it is said to be a kind of constant filter. These I's are very important here also. Otherwise, the filter is said to be dynamic if we have something different. That means different values are coming. From the very definition, a smoothing can never be constant. Rather, it has to be dynamic in all instances, because we can see that this is the upper limit what we are taking I minus 1, which is actually dynamic to this particular state. That means at the particular level where we are, we have to take the upper limit in that sense. So it is always a dynamic thing. Now, I just first come to the point of positional importance, because we are now here introducing this newfangled developments, and we will be proceeding to first try to comprehend what are the meanings of these things. Then we will try to incorporate the matter. What is their positional importance? Let me say something here. For positional importance, the weight associated with the current position, that means if I at the ith position, this current position should be the ith one, must be greater than the other weights. That means what we can have here, whenever I'm saying Wi0, because I put here J0, that means at the current position, this is the J, this is giving you the signature that where we are from the current position. If 0, that means instantly we are at the current position. If J is 1, that means this is a past value. If J2, that means we are past to past, and then so this way we are actually backward progression is going on. So in that level, whenever we are talking of the positional importance, we must understand these W0, Wi0, better to say, this is going to be greater than all such Wij where these i's are taken from k plus 1 up to n. And for the admissible, whatever be the admissible j are there for the present discussion, we should have these particular thing. And if it is being done, then I would say that positional importance is maintained for both the cases of filter and smoothing. So next we have what is about the convexity of filter and smoothing, because that is very essential here also. Whenever we are talking about the particular consideration of these convexity, that means we are taking the sum of all the possible weights what we have taken in this particular discussion, that would be equal to 1. And if that happens, then I will say this process, whether it is a process of filter or a smoothing, this is supposed to be a convex one. So what happens here, to have a convex filter or smoothing, the sum of all the associated weights at any ith position must be unity. That means the 1. So if we want to have a convex filter, it means that I must take the summation from this up to the k prime, 0 to k prime, this Wij must be equal to 1 for all such I from k plus 1 up to n, and this k prime is lying between 1 to k, as we have already mentioned. And if we want to have, on the contrary, a case of convex smoothing, we should have the summation in the different form, something different. I should have the summation from I0 to these I minus 1, already mentioned about the upper limit. These Wij must have the summation as 1. And this is again true for all such I k plus 1 to n, and k must be greater than equal to 1. Now let me come to the very essence. What is the newest development here, what we have done? The introduction to the position interactive filter, what we have done here at this moment. So whenever we are talking about the position interactive filter, the corresponding weight Wij, as we have introduced in the previous equation 1, that is the introduction to the filter, we should have this Wij is equal to this, I have taken in that way, Aij plus Bi plus Cj plus D divided by Ei plus F. So many different, you can see 6 different parameters I have taken for I this k plus 1 up to n, and j from 0 to k prime. And these 1 and k, these are the boundaries for these k prime. But we must remember that all these E and F, they are not simultaneously 0, because if that comes in that way, of course the denominator part is 0, which is not possible or admissible here. So let me have the significances of these 6 different parameters what we have taken. The first A, this is going to give us the idea of the interaction between the current allocation point and distant point with the distance j along the left side. When we talk about the B, it is the contribution of current allocation. When we talk about the C, it means the contribution of the distant point with distance j along the left side. This is the past one. And D is the scaling from this particular acting as a bias term. And these E and F, these are also very important. These are going to give us some positional characteristic. That means where we are, these are having some positional values for this E and F with this E and F method. We are now coming to the other aspects very quickly to demonstrate the matter. Constant position interactive filter. In this case, what happens? We are actually taking into account this filter, and these corresponding weights are going to be independent of I. In that case, I will call this as a constant filter. Position interactive also, and we are having hence in this case A0, B0 and C0 as well as F is not equal to 0, and in that case I would have this particular Wj, which is the weight at this moment. We are having this as Cj plus D divided by F, and we now put forward this issue. If this structure is taken into account, we put forward this issue over the particular process of the filter already we have demonstrated, and that is going to give us the value as fi as xi already we know between 1 to k. But whenever we are taking the sum as it is being demonstrated here, I'm not going to depict or say all the words or the particular symbols there. This is quite visible. You are having this particular summation as presented in 7 when we are putting the values of wj there. And as an example, I can see that we are putting the values in particular C as 1, D as 1, F as 1, K as 1, K prime as 1. And we are taking these values there, spreading with the values because we know already A, B, and E, these are taken to be 0 for the constant filters. And we are having in this particular example, Wj is j plus 1. So accordingly, this equation 7 is coming very quickly, and we have this result. Let me come to the next aspect of constant convex position interactive filter. Convex means we are adding the summation equal to 1. So in that aspect, you can see the equation 8 is also there, which is saying the summation here that should be what we have taken in this 6 form, it would be also 1. And to have this particular thing as unity, you can see this particular expression is coming out. And just to mention that we have to have a generalization of this result for constant convex position interactive filter of order 1. Let me suppose we have k prime equal to 1. Order 1 means we are taking this values of k prime how far. If this is k prime equal to 1, that means order 1. If we take k prime 2, that is order 2, etc. This way. I took this example as k prime equal to 1 of order 1 filter. So I will be having here this equation 10 as C plus 2D. This is equal to F in this particular result in particular. And we put forward, just for an example, in this order 1, let me take C1, D1 and F3. And we are having these results very quickly coming. This as equation 11, what is coming as a demonstration of the result of the design of the filter in this aspect. Now, for a constant convex position interactive filter of order 2, by the similar manner, I have to produce here k prime equal to 2. And this is going to give us the value. This is expression what we are getting 3 multiplied by C plus D. This is coming out to be F. And let me take one quick example just to demonstrate the matter. We take C1, D1 and F equal to 6. And that is going to give us the result as given in this equation 13. So these are quite, these results are quite conspicuous, what I believe. And these are coming from the very demonstration, from the very new result what we have developed. This is kind of what is called the position interactive filter, and later on we have idealized the matter as a smart filter or smart smoothing. So what we are having at the very next level, we now idealize the matter of constant position interactive filter obeying positional importance. So let me now introduce a matter of positional importance, and that is called as a constant smart filter. So for that issue, as I mentioned, I would have the W0 at the current position value weight. It should be greater than all such Wj's, and that is going to give us D by F greater than this Cj plus D divided by F. And this is going to give us this result as demonstrated in 14. This is a logical one. We can see so many things are there, so many options are coming, and we have to accept all these options accordingly. So it is going to give us C by F less than 0 and J is positive, and this finally gives. Either we are having the condition C less than 0 and F greater than 0, or vice versa, C greater 0 and F less than 0. So we can accept any one of that, and that will give us the result. And if we want to have the convex constant smart filter, what is happening here? We are taking one example here, C as this minus 2, D as 3 and F4. And this is going to give us this result accordingly. This is one demonstration here that is being done. And for a convex constant smart filter of order 2, what is happening? Let us take the value as C minus 2, D3 and F equal to 3. This is going to give us this equation as 16. Let me come to the aspect of dynamic smart filter. In a dynamic filter, all the associated weight depends on the both I and J. a dynamic position interactive filter of order K prime is governed by the very first one, as I mentioned, and the fifth equation already being demonstrated. And further, in a dynamic smart filter, additionally, positional importance is to be satisfied apart from these two issues. So if we want to satisfy this positional importance, as we know, we should have Wi0 greater than Wij. This is a generalized matter. This is not a constant one. So we should have these result as it is being followed. These particular left hand side is for Wi0. These right hand side is for Wij, and this is giving us this particular ratio is coming out to be less than 0. And to satisfy the matter for all such cases in a general condition, we should have either these ai plus c less than 0 and ei plus f greater than 0, or the vice versa. That is being done in 17. And with certainty, if we want to have a generalized result here, I should have either a less than equal to 0, c less than equal to 0, e greater than equal to 0, and f greater than equal to 0, or the opposite one, a greater than equal to 0, c greater than equal to 0, e less than equal to 0, and f less than equal to 0, such that obviously we should have altogether both e and c not going to be 0, 0, and not all these e and f going to be simultaneously 0, 0. Okay, so in final dynamic smart filter of order K prime is defined by these three different results as we have done here. I take this example of this one. I put here a minus 1, b1, c minus 1, and d2 and e1, and f equal to 5, satisfying all these conditions. And we take the first order K prime as 1. So we are having this result as given in this 19. And the corresponding filter is coming out to be here in this equation 20. Let me come to the dynamic convex smart filter. That means additionally we are taking this issue of summation equal to 1 this way. So if we put forward the summation equal to 1, we are having eventually this result is coming to be complicated one. This is the particular theme what we are having, and to satisfy every aspect of this one in general. Okay, so at any position, obviously we should have these particular things as given in 22, or equivalently we can just put a and c with this forms of b, and these results are coming here. So we are having these results to satisfy in general. I must have these b greater than equal to e greater than equal to 0, and d greater than equal to f greater than equal to 0, or the vice versa, that is b less than equal to e less than equal to 0, and d less than equal to f less than equal to 0, such that we must admit that both these e and f are not going to be 0, 0 simultaneously. So this is evident that the dynamic convex smart filter of order K prime is governed by all these four equations. This is the last one, the condition for these ABCD E and F. Example is I put here B as 2, D as 3, E as 1, and F as 1, and we put K prime equal to 3. There's a third order filter is being taken. So we are having the results for A and C accordingly, and this result is coming for the Wij. This is the general weight results what we have for this case. So the corresponding dynamic convex smart filter can be designed by these equations 26. Now one very simple example I want to produce here. This is about the Kalman filter as position interactive filter. We know this is a very popular one, Kalman filter. In case of Kalman filter, we know this the design that this is a one single order system. We are having f1 equal to x1 only, and this is the next results from I1 to n. We are having 1 by I, this is xi plus 1 minus 1 by I of xi minus 1. And you can see here in general, if we just take into account this proposed formula of the smart filter, and here we put k equal to 1, k prime equal to 1, a as 1, b as this 0, and c as minus 2, and d1 and e1 and f0. We just arrive at Wij as this, and this is going to give us these results accordingly, very similar to the Kalman filter. So this is being proposed here that Kalman filter is nothing but actually one kind of particular result coming out from the proposed system as a development of the positional interactive system. But there is one difficulty here. I have already mentioned that one. This is not a case of, what should I say, a case of this is position interactive, but it is not supposed to be a smart filter, because in case of a smart filter we must also arrive at the condition that should satisfy the condition of the positional importance. This is not being done in this case. So I just consider this case of Kalman filter as only a case of positional interactive system, but it is not an example of a smart filter. So let me come to the position interactive smoothing. On the other hand, what we are doing here, very similar things. I propose the same kind of Wij here, aij plus bi plus cj plus d divided by ei plus f. Same kind of these particular contributions what we are having for the 6 parameters. But something is different, as I mentioned, that the upper limit is there conditionally depending on i's. So we are having something different results accordingly. So what we can see here, as we know that for having dynamic smart smoothing, I should have wi0 greater than wij, and this is going to be true for all such these i's from k plus 1 to n, where this k greater than or equal to 1 and j equal to 0 to I minus 1, because we are taking the limit from 0 to I minus 1. And if we want to produce the idea of a dynamic convex smart smoothing, this is going to give us a convex. The sum of wi is equal to 1. This is going to give us this result. And accordingly, we can have this particular summation, as we can see, and a complicated result is coming as 31. But we must remember this is true for all such positions. It is irrelevant of these i's. Every position I should satisfy these parallel equations. So we must have in general this a equal to 0, this particular 2b plus c minus equal to 0, as well as 2d minus c minus 2e, that is 0, as well as f equal to 0. And after simplification, we are trying to minimize the number of independent parameters. So we are having these results accordingly, as we can see here. I'm not going to depict these results. And accordingly, we can have these particular issues satisfying all these conditions. We should have either c less than 0, e greater than 0, or the opposite one, c greater than 0 and e less than 0. So in this process, we are having these example. This is a structure equivalently for this, and this can be written in the further shape like this. So one thing you must understand here is we put something g as c by here, this particular thing what we have taken, and this is going to give us this less than 0, because we get this c and e, the opposite signs. So we are having the structure in this form. We just minimize the total number of parameters just to make a simpler version of this one. So we take this way. And let me put one example that we put, say, to g as minus 1, and accordingly we can have the result of the structure of this convex smart smoothing like this. So some concluding remarks on these issues what we have tried to develop. The proposed versions of filter and smoothing are parametric in nature, and these are basically linear denoising process, as we can see here. These take care of the individual contributions of the different observation points and the mutual interactions between them. This is possibly enhancing the effectiveness of the corresponding denoising process, as it captures more adaptation in the governing mechanism. But there are certain limitations and demerits of the present model. Firstly, I should say this model doesn't include the detrending strategy, because trending is a very harmful thing in certain cases, but we are not taking any measurement of the detrending in the strategy. Secondly, it doesn't take care of the preservation of memory of a data, which is seriously affected in the process of denoising, because if you have we can notice that if we're having previously in the observed data some memory of 3 or something like that, or 2, or this is 4, whatever it might be, whenever we are adopting some form of this mechanism of denoising, it is being perturbed. 3 becomes 4 or 5, or 3 becomes 2, something like that. So in most of the cases, it is being seriously affected. So we have not taken care of these issues also, and future matters should be taken care of this way. Thirdly, though it's a simple exponential smoothing, I have not given the example here, but we must notice simple exponential smoothing is a very popular form of exponential smoothing. But this is also very effective, because here the conditional case of the positional importance is being maintained. But the problem is we cannot understood these particular process by means of the current smoothing result what we have established. But possibly it requires some alternative model to understand the same, because we are having the issue that though we can understand Kalman filter as an example, a particular example of the process of positional interactive filter, but unfortunately we cannot derive the simple exponential smoothing, though it's very popular and effective one, and of course some way better than the Kalman filter, I should say. But we cannot unfortunately derive these expression of simple exponential smoothing from the very context of our proposed model of generalized model of the position interactive smoothing. And lastly, no discussion has been placed on the optimization of the parameters involved in the model to excel the process of the denoising. In future, we should take care of these particular pertinent issues to have more useful smart filter and smart smoothing. So these are the references what we have actually used for the present work. This is the end of this particular list. but I must say most of this particular lecture or content of this lecture is being published here. As you can see here, this is one chapter. This particular chapter is having the heading of Smart Filter and Smoothing, a new approach of data denoising. And this is being published as a book chapter in the book of noise filtering for big data analytics. It's a De Gruyter publication, and myself is one of the editors with Dr. Shovik Bhattacharya. So if you want to have further reading, you can just go through that one. So thank you very much for your kind attention. Thanks to all.